Going to finish up from day 36. We left off having a sine wave, 1 kilohertz, and what was it? 1 kilohertz, 1 volt amplitude, 0 DC offset. We simulated this, ran it for 5 periods. The stop time should be, this says microseconds, but it should be 5 milliseconds. And the time step, I prefer to use 100x time step, so 1 millisecond divided by 100 is 10 microseconds. This is what we get. Add a DC offset of 1 volt and redo it. So here is a DC offset of 1 volt right there. 1 volt, 1 kilohertz. We have everything here. I'm going to run the simulation. 0 to 5, 10 microseconds. Run this time domain simulation. The output obviously is centered at 0 or 1 volt. It goes up by 1, goes down by 1, so it goes from 0 to 2 volts peak to peak. Not very exciting. So next up, we're going to consider how we can get rid of this DC at the input to the amplifier, because I don't want it. Your last homework problem has some DC. It's the DC offset of your op amp. It's homework number 14, but you don't know what to do with this, perhaps. All right, so let's use a series capacitor. You remember that capacitors behave as open circuits at DC, but they behave like short circuits if the frequency is large enough and the capacitance is large enough. So let's add a series capacitor, and we'll just choose 5 picofarads because that's what I want for today. It's part of the rest of the example. So stick in a capacitor. This is 5 pico. Wire it up and re-simulate. What's up with this? That's weird. Do you see how that's weird? That's really weird. So here's -5, +5. This is hooked up, right? Yeah, that's hooked up. Here's my power supply. Run the simulation again, and what do we get? We get the output, which is blue here. We have Vn minus Vs. Bunch of weird things. I'm going to not plot that. Try it again. The output is pegged at -5. Of course, the input here is going around, Y going around 1 volt. That's not a surprise, but what's up with this? Well, there's 2 reasons. The main reason, well, many reasons. So we're going to look at this. We don't have any way to specify initial conditions across this capacitor. So let's, in CircuitLab, so let's add a time-controlled switch to this, and this switch will be closed at time equals 0, and then at 1 millisecond it will switch to open. So you see the arrow there. All right, rerun this simulation, and we get, well, we get a sine wave, and it's not clipped or anything, but we didn't get rid of the DC. We didn't shift this down by 1 volt. It should be shifted down by a volt. Why does it not do that? Well, we still didn't get our initial condition right across this capacitor. Let's just leave that for now. If you go back to this document, you see we have this. Did that again. What's up? Well, forgot the initial conditions. Here's our simulation here. And the switch is closed from 0 to 1 milliseconds. Switch opens, remains open. All right, you should see this for yourself in your own simulation. Please do this yourself. Did it get rid of the offset? No, it didn't. Let's go back to that simulation again. Do you see something a little weird? The output looks like it's drooping. By the end of the simulation, it's like shifted down a little bit. Okay, that's a little interesting. All right, so let's simulate this thing for an entire second, but leave the step time the same. So step time is the same because I still need to see my sine wave. I want to go for an entire second. That is 1 second. Run this thing. Actually, I want to, hold on, add an expression. I'm going to call it V in minus Vs. We'll ask for this here in a minute, but might as well just do one simulation. And it's going. We'll go back to this. So one reason why our output didn't shift at 0 to 0 because of this capacitor was when this capacitor is shorted, obviously the voltage between the left side and the right side, S and node in, are the same. So the moment that I open this switch, that initial condition will stay the same. So there's still 0 volts between S and in. And that means S equals in, add a millivolt to this, and there's our output. That's why we don't shift by 1 volt. We would need an initial condition of 1 volt across this capacitor, 1 volt, the right side lower than the left side. We done with that? Oh, why didn't we do that? Do we have to wait? Keep the browser open for it to keep running? Maybe not. Here it is. What? This is weird. This is really weird. So here's my sine wave. It goes up and down. You can see that it starts centered around 1, and it just falls and falls and falls. If I zoom in here and I look at this, I'm clipping. I'm clipping at -5. Why are we clipping at -5? Well, that's my power supply, remember? Here it is. How many time steps did we ask the simulator to compute? Well, if we go back to our time steps, this is 10 microseconds in 1 second, so this is 100,000 simulation steps. Of course, it took a long time. How many cycles of the input signal was this? This is a kilohertz for 1 second. That's only 1,000. But when you plot it like this, that's what it looks like this. All right, so we have Vn minus Vs. This is the voltage across the capacitor. Here, this gold line down at the bottom is the voltage across the capacitor. You notice that it is constant-ish. We could zoom into this and see if, I mean, it looks pretty constant, I think. What's going on? What's the slope of this? The slope is the interesting thing. So it starts out at 0, and we'll make this easy on ourselves. It goes to, wow, it goes to -10. Let's see, -9.8 at, let's just say 10, round it to 10, -10 volts in 1 second. So its slope is -10 over 1. Okay, so this is -10 volts per second. What's the capacitor's equation? Well, that's IC is C dV dt. I just computed dV dt. So this is IC is 5 picofarads times -10 volts per second. And actually, if you take farads times volts and you divide by seconds, you get amps, which is a little weird. Equals, we'll go like this, so equals -50 pico amps. That, does this make any sense? We need to consider what this 50 picoamps means. Let's go back to our circuit. I plotted using an expression, add expression button, V in minus Vs. So that was a in minus S. So the right side is plus, the other side is minus. That means passive sign convention means that arrow current is going in a positive direction to the left, but I got a negative number. That means the current's going to the right. It's going to the right, out of this, through here, into the, what? Into the op amp. Oh, check this out. Look at this input bias current. The input bias current is, in fact, 50 picoamps, and apparently that means going in, because otherwise our signs wouldn't make any sense. Okay, well, this is bad enough because my simulation, first of all, it goes for a long time. Let's do 300 milliseconds. We don't have to wait so long. how do we deal with this input bias current that goes through the capacitor, charges up the capacitor? Well, the answer is that I need some place to allow that current to flow, which is this, which is through a resistance. Let's put this as 1 mega ohm. Sounds like a lot, but remember, this is the input bias current. This is 50 picoamps. 50 picoamps flowing through 1 mega ohm. That's 10 to the 6. And divided by 10 to the minus pico is 12. So this is a microvolt, or 50 microvolts right here. Okay, let's try this out, simulate, see what we get. I'm waiting. I don't like to wait. V out. Where is V out? V out is, let's, what? Why is it so small? Why is it so small? This is 5 picofarads. This is a pretty good high-pass filter. We could compute what the frequency response of that is, or the cutoff frequency, but I'm just going to make this 1 microfarad. Now we don't have to wait for this to charge up. That's why I made the capacitor so small, so we could see that effect. Otherwise, the slope is very shallow, and you wouldn't even notice this on a simulation. So we'll run the simulation again, 300 milliseconds. Every 10 microseconds, we'll see what we get. Why is it still slopey? I don't like this. Why is it still slopey? Because I have the switch here. Now, go back here. I can delete this switch because I can now solve this for DC. At time equals 0, the left side is 1 volt. The right side of this is happy to be, this would be negative 50 microvolts. We'll zoom in on that here in a second. So if I simulate for 30 cycles, I'm getting a little impatient. Here we go. Here's our input. Here's our output. Our input is shifted up by 1. Our output is centered around 0. Now I'm going to zoom in to the very first timestamp here. And if I zoom in and look at this, this is 950 microvolts. Is that a millivolt? See how it's a millivolt minus 50. This is 950 microvolts. Well, let's go back at our circuit again. 950 microvolts. This is 1 millivolt times a gain of 1. You know about superposition. But the node right here is minus 50 microvolts because of the input bias current heading to the right. So if you take minus 50 microvolts plus 1 millivolt, you get 950 microvolts. See how the subtraction goes there? Now, in general, don't presume that you know the sign of even the input bias current unless you have good information from the data sheet to know the sign. Remember that that sign is usually it's usually given as positive because we talk about magnitudes. So we have shown what you can do by adding a capacitor here to shift DC to ignore it, and then we still have to have current that goes DC current path for our input bias current for the op amp. Thanks for watching.